Welcome, ladies and gentlemen, to lecture number 1 in the course EEE 4682. This is a course in basically looking at communication systems. And our first lecture, which is basically Introduction to Communication Systems, we'll look at the following issues. We'll look at a brief introduction to the topic. We'll look at the elements of the communication system. Look at the frequency and bandwidth, classification of this communication system, and some of the transmission techniques adopted in these communication systems. Now, a communication system conveys information from its source to destination, and there are several examples of these communication systems. We have the public switch telephone communication system, the television communication system, radio communication system, the cellular communication system, satellite communication system, with the Wi-Fi, with the WiMAX. Each of these communication systems basically performs a function of conveying information from one user to the next, or basically from the source and the destination. A communication system is composed of the following elements. We've got the information source, the input transducer, the transmitter and the receiver, and in between you've got the channel, and this channel is usually susceptible to noise, and then you've got the output transducer. So in the next slide, I'll basically now explain in brief each of these elements, starting with the input transducer. Usually the source is analog or digital, and what the input transducer basically does is to convert the message produced by a source to a form that is suitable for communication systems. For example, you may have speech waves being converted into voltages using a microphone, and in this case, the microphone therefore will be the input transducer. So a transducer is basically any device that converts energy from one form to another, and in this case, we're talking of speech wave being converted into voltages. Next, you've got the transmitter. Basically, the transmitters couples the message to a channel, and there are several operations that are performed by the transmitter there. The transmitter can amplify the signal before it does modulate, and it can also modulate, basically adding a carrier to the baseband signal, and then this modulated signal can then be amplified and transmitted. Modulation also encodes messages into amplitude, phase, or frequency of the carrier signal. And so we may talk of amplitude modulation, phase modulation, frequency modulation when we refer to analog modulation schemes, or we may be talking about other digital modulation schemes such as QAM and the like. Now, the advantages of modulating is basically to reduce noise and interference. It also enables multiplexing and channel assignment. All these are done in the transmitter. And a good example of a transmitter could be a television station, a radio station, a web server. All these are basically different forms of transmitters. Next, we've got a channel. Once the information has been, sent from away out of the transmitter, it will enter a channel. This channel could be a physical channel. It could be an air interface or air channel. So physical medium that does the transmission of basically the information from the transmitter. And we have got several examples, like I've mentioned there. It could be the air, wires, coaxial cable, radio waves, laser beam, fiber optical cable. All these may be used as channels for basically moving information from the source to the destination. So every channel introduces some amount of distortion or noise and interference, and that's why later on in our lecture number 2, we'll discuss about noise and interference as it pertains to communication systems. Then we've got also the receiver, which basically extracts the message from the transmitter via some channel, and it will also perform amplification, demodulation, and filtering functions. And usually the goal of any receiver is to receive the output and possibly delay version of the message signal. And we've got several examples of receivers. We've got a TV set, it's an example of a receiver. A radio set can also be called a receiver. Your web clients such as your smartphones, your laptops, all these are examples of receivers. So any device that receives information from another device basically becomes a receiver. Now I must be quick to mention at this stage that most of these modern devices, can perform the function of a transmitter and also the function of a receiver. Very few devices are purely transmitters and purely receivers. Your smartphone, for example, is both a transmitter and a receiver. In such devices which can perform both functions of transmitting and receiving are basically called transceivers. The output transducer basically converts electrical signals into the form desired by the system. And if you're talking of basically a radio receiver, once the information is received, the output transducer will convert the radio waves into an electrical signal, and again, from an electrical signal will be converted into sound, from the source. So basically, we have several examples of transducers. A loudspeaker is an example of a transducer. A laptop, a PC is also an example of an output transducer. Next, I want us to talk about frequency spectrum. Now, spectrum or frequency spectrum is the most precious resource in communication systems, and the frequency spectrum has to be shared by a large number of users. And when we talk of frequency spectrum, this is basically a range of frequencies that are available for use. And this range of frequencies can be used in AM radios, in frequency modulation radios, television, cellular telephone, wireless local area networks, satellite, and air traffic controls. So by definition, basically, the frequency spectrum is a range of frequencies that are available for communication purposes. The spectrum of a signal is the range of frequencies that it contains. For example, you have the first signal there, VS1, and VS2, which is the second signal, VS3. Each of these signals, will be transmitted at a given frequency, given by F equals 1 over T. So when we calculate for the first one, you've got F1 over T1, which is 1 over 2, 0.5 Hz. F2 will be 1 over T2, which is 1 over 1 Hz. And F3, you've got 1 over T3 equals 1 over 0.5, which gives you basically 2 Hz. So what would do the frequency spectrum for such is basically a range from 0.5 to 2 Hz. So it's basically from F1 to F3 that gives you the spectrum. It's a range of frequencies that are available for communication purposes. Related to frequency spectrum is what is defined as bandwidth. And the absolute bandwidth of a signal is nothing but the width of that spectrum. So if I know the starting frequency and the end frequency, the difference between the start and the end frequency gives you the bandwidth. In this case, F3 minus F1, which is 2 minus 0.5, giving me a bandwidth of 1.5 Hz. Next, I want us to talk about how do we classify this communication system. Communication system can be classified as unidirectional and bidirectional communication, analog and digital communication system, baseband and communication with modulation. And then you can also classify it in terms of wired and wireless communication systems. In the diagram here, basically I'm illustrating an electronic communication system And you can see the three basic classification there: unidirection or bidirectional communication, nature of information signal, techniques of transmission. And under unidirection, you can have what is known as simplex communication system, half duplex, as well as full duplex. And then the nature of information signal, there where you classify it in terms of analog and digital, and also based on the technique of the transmission, where you classify it in terms of baseband transmission as well as communication using modulation. Now, for transmission in one direction and for communication in both directions, we basically talk of unidirection if it is basically in one direction, and a good example there is simplex, and for bidirectional, there are two there. You have half duplex as well as full duplex. So bidirectional means that information can flow from both directions, while unidirection meaning that you can only transmit information in one direction. So simplex, in these systems, the information is communicated in only one direction. And a good example is when you are transmitting information, say from a radio or broadcasting station onto a radio or TV set in individual customers' homes. So that's a good example of simplex communication. Information will flow from this radio or TV broadcasting system to a radio receiver at one's home or a TV station at one's home, but there will be no information flow from the radio set to a radio broadcasting station. So that's simplex. In half duplex, it means that you can transmit as well as receive, but not simultaneously. And a good example is the radio system such as those in military, firefighting, the citizen band, as well as amateur radio. All these are examples of half duplex. If you're going to join any of these in the military, for example, you have those Roger phones, radio station, radio receivers. Those are basically used for half duplex communication. Now, in full duplex communication, it means that you can transmit in both directions simultaneously. And the best example of full duplex communication system is a telephone system. Okay, so moving on, let's look at some of the transmission techniques. As you transmit information from the source to destination, you need to employ some of the techniques, and the key techniques is modulation, where you add the carrier to the baseband signal in order to enable you transmit information over a long distance, and as well as to minimize interference and noise. But the other technique is multiplexing, and under multiplexing, you've got frequency division multiplexing, time division multiplexing, you've got code division multiplexing, and orthogonal frequency division multiplexing as well. So let's discuss each of these techniques in a bit of a detail. The modulation technique, we'll discuss it it should be in lecture number 3, but let me talk briefly about multiplexing technique. And under here, like we said, we've got frequency division multiplexing, time division multiplexing, code division multiplexing, as well as orthogonal division frequency multiplexing. Now, frequency division multiplexing takes advantage of the fact that the USIF bandwidth of medium exceeds the required bandwidth of given signal, while time division multiplexing takes advantage of the fact that the achievable bit rate of a medium exceeds the required data rate of a signal. And so discussing this in a bit of a detail under frequency division multiplexing, basically, this is a situation where within a given time, you are able to transmit several frequencies, several channels. Each of those channels or frequencies F1 to F6 representing a user. So several users can transmit at the same time as long as they are separated in terms of frequency. So that's what is meant by frequency division multiplexing. It means you're able to transmit at the same time several users, separated by frequencies. These frequencies representing a channel or user, and these are able to transmit at the same time because they're doing so at different frequencies. Therefore, there will be no interferences, there will be no distortions, because each user will be operating at a different frequency. Next, you've got time division multiplexing. This is where you are sending several users or several channels separated in time. They are able to use the same frequency. They are all using the same frequency, but this frequency, the only separation there is time. And so each user is given a time slot. Each user is basically given a time at which to transmit. So they are transmitting at different times, but using the same frequency. That's time division multiplexing. Then code division multiplexing does not rely on so much on the physical properties such as frequency, which we saw under frequency division multiplexing, or time, which we saw under time division multiplexing. But basically, each sender is assigned a unique binary code, which we call C1 in this case. And that unique binary code is called the chip sequence. So at any point in time, each sender has a value transmit. So if the sender has some information V1, this V1 is being multiplied by the unique binary code. And so in that way, each subscriber will be transmitting, even if they are transmitting at the same time, same frequency, but because they're using a unique binary code, therefore, the transmission will be possible without any interference and without any noise. The sender transmits at the same time, and the values are added together. So each of these senders will transmit at the same time, and their values will be added together. The illustration of code division multiplexing from this diagram, you will notice that what we have here is a situation, say we have sender A. Sender A is given a unique code, 10, and he's sending that data there. And as he's sending this data, because he's sending using a unique sequence, chip sequence, there will be no interference or noise emanating from sender B, who equally has a different unique code for transmitting the data. So these two can be sent at the same time without any interference, as long as every sender is given a unique code, or basically the chip sequence. So basically, that's how you achieve code division multiplexing. The next one here we'll consider is basically orthogonal frequency division multiplexing. Under OFDM, the basic idea basically here is to divide the achievable spectrum. You divide a given frequency into several sub-channels or several sub-frequencies. And each of these sub-frequencies, they will be overlapping and orthogonal in nature, and you are able to basically transmit without any interference because of the orthogonality part and the overlapping principle that is employed in the orthogonal frequency division multiplexing. Now, I will not say much on OFDM because I've given an assignment. Basically, this is where you get your first assignment to look at orthogonal frequency division multiplexing in more details.